Okay, in this video I want to have a look at exponential equations and logarithms and getting a straight line from an exponential graph. So if you remember, in the earlier video we looked at the concentration versus time graph for exponential decay, starting off at an initial concentration C0, and we saw that we had exponential decay, and that was given by this equation. Now, say you take some data, you've given a drug and taken samples and measured the concentration over time, and you plot it on a graph like that. You might want to know whether or not that follows single exponential decay. And one very quick way of knowing is to actually take logs of the concentration, so ln C against time. And what you find then is that you actually get a straight line. So it starts off at ln C0, and you get a straight line graph when you use this log transformation. And that straight line graph is telling you that your data is following single exponential decay. And furthermore, the gradient of that line is the rate constant for elimination, Ke. So I just want to show you mathematically why that is. That's the key point, but let's have a look at the maths behind it. So C equals C0 times e to the minus KET. So the first thing I want to do is show that this actually gives you a straight line on a log plot. And to do that I need to take logs of both sides of this equation. Okay, so what I've got here is C is equal to C0 times e to the minus KET. I'm going to take logs of all of that. So ln, I'm going to use natural logs because that's tradition. Ln C is equal to ln C0. And if you remember, if you've got two terms that are multiplied by each other, you can add the powers, and the log is the power to which the base is raised. So it's ln of C0 plus ln of e to the minus KET. Now, if you remember, the log is the power to which the base is raised, so ln of e to the minus KET is just minus KET. So ln C equal to ln C0 minus KET. Okay, so here is my y term. I've plotted that on the y-axis. This is what you might call c. You know, if you remember your equation of a straight line, y equals mx plus c. Okay, so here's y equals, I've just done it the other way around, c, and this is the gradient m, and that is the x value. Okay, so here we've got y equals c minus mx. That's just because the slope is going down. Okay, so this is showing you that if you plot ln c against t, you'd expect the equation of a straight line, and the y-intercept is the natural log of C0, the initial concentration, and the gradient is a value for Ke. So this is a quick way, easy way of getting an estimate for Ke. You can then use the Ke to work out the half time, because the half-life is 0.693 divided by Ke. So let's just have a look at why that is then. Let's do a little derivation of that. Okay, so when the time is equal to the half-time, the concentration is equal to half the starting concentration. That's the definition of half-time. So we can put those values into our equation. We've got a half C0 for our concentration is equal to C0 e to the minus Ke times T half. And actually I've got C0 on both sides, so I can divide both sides by C0. and then they'll cancel out and I don't need to worry about them. So now I've got a half is equal to e to the minus ke times t half. Now I'm going to take logs of both sides of that. So I'll have ln of a half equals minus ke times t half, and ln of a half is ln of 1 minus ln of 2. That's the rules of powers. And ln of 1, well, that is 0. So you just check on your calculator if you want. So we're left with that relationship there. I can multiply both sides by minus 1 to get rid of that minus sign. So I'll just do that. And then we can divide both sides by ke, because at the moment here I've got ke times t half, so I just divide by ke and that will cancel out. So t half is ln of 2 over ke, and ln of 2 is just 0.693 over ke. Okay, so that shows you how we got this original relationship between the half-life and the ke, and we've also shown mathematically why, if it's first order single exponential decay, that you get a straight line on a log plot.